number 8 from 10.4? Okay. What did that one say?
That one from the National Academy of Science reported in a 1996 study that 40% of research in mathematics is published by United States authors.
Okay, so 40% of math by US. Okay.
Mathematics chairperson of the prestigious university wishes to test the claim that this percentage is no longer 40%.
Test that 40% is wrong. Okay.
He has no indication of whether the percentage has increased or decreased since that time. He surveys 130 of the latest articles published by reputable mathematicians research journals and finds that 62 of these articles have U.S. authors.
62?
Yes.
Okay.
Does the seven support the mathematics chairman's claim that the percentage is no longer 40%? Use a 0.1 level of significance.
Off of this point 1. That it?
Yes.
All right. So, what do we start with? What do we always start with in chapter 10?
No, an alternative.
Yep. The whole What's assumed to be true? 0.4
Equals 0.4. Equals not equal.
Awesome. There's our ho and our ha. So far, so good.
Z-score.
Uh-huh. Theoretically, what's my Z critical value? Or you can do the p-score, whichever way you want to do it.
Z is 1.645.
What was that?
1.645.
So again, we're going to reject the null hypothesis if our Z score is more than 1.645 or less than negative 1.645. Now, how are we going to calculate our Z value?
P hat minus P all over that stuff.
All right, what's P hat, folks?
62 over 130.
Give you 2 decimals.
Like 0.48.
0.48.
It looks like it's true.
All right, so plug and chug. 0.48 minus 0.40 theoretically. All divided by the square root of 0.4 times 1 minus 0.4. That's a decimal 0.4. All over, what was n? 130. Times 0.6 divided by 130. Did you get 1.86 for your z-score? 1.86. And just so that you can do it, folks, what is the p-score for 1.86? Please remember that you always just look up the negative of that value. Negative 1.86. And since this is a two-tailed test, what are we going to do with that number? So our p-score for this test is 0.0628. What was our alpha? 0.1. Is our p-score less than our alpha score? Yes. Therefore, what do we get to do? You can reject that null hypothesis and assume that it is true that the average percentage of mathematical articles being created by US people is not 40% anymore. And again, you can look at that either way you want. Is P less than alpha, or is our Z-score greater than our Z critical value? Either of those should give you the same result. All right? Not bad? Any others?
My number 10, Mr. Labs.
What was that?
My number 10, Mr. Labs.
Same section?
Yeah.
Ah. What does number 10 say?
Sleep experts believe that sleep apnea is most likely to occur in men than in the general population. In other words, they claim that the percentage of men who suffer from sleep apnea is greater than 8%.
Percent of men is more than 8%.
Yes.
Okay.
Then to test this claim, one sleep expert interviewed 75 men and determined
How many?
at 75. 10.
10? Oh, sorry. I didn't hear the 10.
Does this evidence support the claim that the percentage of men who suffer from sleep apnea is greater than 8%? Use a 0.05 level.
Significant is 0.05. All right.
So, what's 0.08 times 75?
0.08 times 75?
0.3?
What, or 6?
6?
6.
0.08 times 75?
So, what's our ho and our ha?
More than one is greater than 0.08.
What are they trying to test? So what do they want to be true? Right, they want the percent to be more than 8%, right? So that's therefore your ha.
Oh.
And again, the number should give that away a little bit, right? Because when you took 75 times 0.08, you got 6, right? And so they're trying to say that it is more, so they're trying to claim that it's greater than that average value of 6. And so since you have a number greater than 6, it begs to reason that the proportion you're trying to test is greater than, not less than. All right. So, again, before we move on, what's p hat?
0.338 minus.
What did that work out to to be?
0.13 repeating.
So what is our z-score, folks? P hat 0.13 minus p 0.08. .08 times 1 minus 0.08 all over 75. That's a 5, I swear. And note it just barely passed our rule, right? 75 times 0.08 was 6. It had to be more than 5. Don't forget that check. Mhm. What's your p-score for 1.6? Again, look up negative 1.6 in the tables.
0.0548.
Yeah.
0.0548. And so is our p-score less than our alpha? Not quite, right? So since our p-score is not less than our alpha, what do we have to say? We failed to reject the hoe, and we must visit the clinic tomorrow morning. Hmm?
Number 16 on table. I just don't know how to set it up.
Hey. Number 16.
Yeah. The City Council of Oxford is thinking of building a road around the city. They want to know if the majority of the residents are in favor of the new road before pursuing the issue further. Set up the hypothesis needed to perform a hypothesis test for a 98% level of confidence.
Test that more than half of population wants this or something like that?
Yeah, the majority would
Wants a road, right? Or a bypass around the road. We all want a bypass around the road. Come on. So what do they want to have? What do they want to show in order to build this road? Majority means more than half, and more than half means that your p is greater than 0.5. That's your hop. Yep. The hope. So majority, just remember majority means half. And so that sort of what drives the 0.5. And that's not necessarily a bad test to try and do. In theory, that's what governments are supposed to do before they do anything, is to actually test the populace and see, is this a majority of citizens that desire this particular government expenditure or whatever it is that they're trying to do. It's one of those where, in theory, I'd like to think that it's done, but in practice, I doubt it ever is. But you don't.
Do we just show that, or do we have to do the whole
No.
secret?
Nope, that's it.
Okay.
That's all you need, because all they really want is what's the hoe in the hop for all of these examples, right? I mean, in theory, you can say, test this at alpha equals 0.10
That's
level.
what I
but
didn't know, if you wanted that.
I wouldn't care. If I saw p greater than a half, p less than a half, I'm in the right ho and ha, and I will be all happy. Not bad? So did you feel like you could get through these, or you are through all of these and you're testing relatively okay?
Did this one include an alpha question?
That number 16?
Oh, yeah.
Yeah, I mean, he said at a 90% confidence level, and so I mean, I wouldn't worry about it because you're not using it to calculate anything, so it's not like it's a big deal. But all right, not bad. Okay, well, if you are done with the chapter 10, 1 through 4, and you want to turn it in, I will, of course, happily take it. If you're still working on it, that is perfectly fine, because I haven't gotten around to grading anything yet, so I have nothing to complain about. Snow is conducive for hanging out by the fireplace, but it was more conducive to watching movies and sleeping than grading, so
Let me know how that works. I did email you a copy of each of these, but I changed some stuff in
okay.
chapter 10.
Cool, thanks. It's much easier if you give it to me in person, because then when I print it, every now and then there'll be pieces that the margins will cut off part of what you write, and I'm like, ah! All right.
Oh, you just gotta turn out 50 pages.
Is that what I have to do?
Yeah.
All right, so. So 10.5 is all about errors. So at this stage, we've been doing some testing for a little while, and we've been either rejecting or failing to reject the null hypothesis. So in these tests that we're taking, folks, what error might we make? So when we get finished with a particular test, we do one of two things, right? So we can either reject the null hypothesis or fail to reject the null hypothesis. So what if we made a mistake? What if one of those tests was incorrect? What would be one of the errors that we could make? Well, no, I mean, I'm not saying that you made a math error. I'm just saying that when we do the test, we do everything correct about the test. But remember, we're doing it at a certain level of significance, right? So like at a 5% or a 10% level of significance. Well, what happens if our case is one of those 10% cases or 5% cases, right? So basically we're saying that 10% of the time, this we're within a 10% error margin. But what happens if we are in the error margin? What error could we make? So if we reject the null hypothesis, what would be our error? What should have we done?
Not.
Yes! There is one of our types of errors, is where we reject the null hypothesis, but we really should have failed to reject it, right? That's one of our errors. What's our other possible error?
The other way around.
Yeah, where you fail to reject the null hypothesis, but you should have rejected the null hypothesis, okay? So there's two types of errors. That's the nice thing about having one of these testing cases where we're just either going to reject or fail to reject.
So are you saying that when we do reject something, we should not have?
Yeah, we really shouldn't have, right? So our testing was all valid, we did all the math right, it's not like we did anything wrong. It's just that our conclusion said we should have rejected it, but in reality, we should have failed to reject it. It was just that for this particular instance, we fell into that 0.05% of the time where it shouldn't be like that, but it really was. So it's just, when you're doing statistics, sometimes the statistics will lie to you, okay? And so you may make an error, okay? So, the cool thing about it is that since it was sort of drummed up by a mathematician, the way they named the types of errors is that you can create a type 1 error, and then you can create a type 2 error. Very mathy way of describing the two errors that you might create. It speaks to me. Whenever I read this, I'm like, ah, yes, a mathematician came up and named something. So much better than having someone who does marketing come up with naming, right? Marketers would have given like a much more cool name to these types of errors, right? One of them would have been, the end of the universe didn't happen, error. And then the other one was, we saved the planet, error. And those would, those would be our, right?
Errors.
Well, I mean, again, whatever. But the fact remains is that type 1 and type 2. Okay, so a type 1 error is when you reject the null hypothesis, but you really should not have rejected. That's a type 1 error. And the type 2 error is the other way around. When you fail to reject the null hypothesis, but you should have rejected H null. Type 1 and type 2. Now, technically, there are names to these, and again, the names are also going to be kind of cool because they're also very mathy, all right? The type 1 error is known as an alpha or a significance or an alpha error, right? So it's an error that's based on your level of significance. The type 2 error, if type 1 is alpha, what's the next letter after alpha? Beta. So the type 2 error is a beta or a beta error. And the way it works, folks, is that these two types of errors, they actually play off of each other, okay? The more you try to stop getting one error, the more you create the probability of making the other mistake, right? So you could think, if you do not want to have a type 1 error, that you could make your level of significance very, very small. So like make alpha 0.001. Get it as small as possible so that you guarantee not to make an alpha error. The problem is that the more you make this error less likely, the more you make the other error more likely, okay?
Like when someone says, I'm 99%, there's 99% chance that you won't do this, but there's a 1% or 0.1%, that's a 0.1%.
Well, it's more along the lines of, think about the confidence intervals back when you had a 99% confidence interval. So if you wanted to say, what's the average age of taking your first drink, okay? And so let's suppose that the average age, we don't know what the average age is, but you ask, say, 125-year-olds, how old were you when you took your first drink of alcohol, okay? And they say, okay, great. Well, the average turns out to be, say, 12. And then if you said you wanted to have a very small error chance, so you raised your level of confidence to say 99%, 99.5%, what you would discover is that your error statistic, the number that you add and subtract to your value, keeps getting bigger and bigger and bigger. So they'll say that the average age that these people took their first drink of alcohol was, say, 12. And then the error statistic would have been also 12. So that the range, the age that a person is between when they take their first drink is between 0 and 24. And you're 99.5% sure that that's true. Well, duh, right? You have now limited the possibility of finding where the actual value is. But now the problem is that you have opened up the door wide to actually saying, hey, yes, I know the range of data is somewhere between 0 and 24. Does that mean that it's 18? Maybe. Does that mean that it's 4? Yeah, maybe. It's equally as likely, right? Because any number between 0 and 24 is the proper average age for when a person had their first taste of alcohol, right? So anybody could claim anything, and that's the type of error you make in a type 2 error. So you can open it up so that you can reduce one type of error so that you're guaranteed to contain the error, but then you've opened up the other side of the value that basically says, well, now you can make an assumption that anything is true. And that's the other type of error that you create. So they play off of each other, all right? And the key is realizing that they do, all right? You can't eliminate both errors. If you reduce your alpha to limit the chance of a type 1 error, you will make the type 2 error chance increase. And there's no ifs, ands, or buts about it, folks. That's just the way it works, okay? Basically what this section is talking about is the fact that statistics are fallible, okay? And this is why you don't pick alphas that are really, really small. You don't pick levels of significance that are 0.005 or something along those lines. Because the problem with it is that, yes, it will limit your chance of creating a type 1 error, but it way, 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 way opens up the door for a type 2 error to happen, right? Where you fail to reject the null hypothesis when you actually really should have, okay? So just be careful with this, and this is also kind of why when you do statistics, you tend not to use the extreme percentages on one end or the other, right? Calculating 99% confidence intervals is poor, just like having an alpha set to 0.01 is poor. It can give you a nice type 1 error limitation, but it just way opens the door to the other side of error happening, okay? And this is why we tend to see confidence intervals or levels of significance right around 5 or 10%, because those are reasonable errors on both sides of the coin, okay? So I don't want to jump down this rabbit hole too terribly far, but just note, folks, when you do a test, if you reject the null hypothesis, you may have made a type 1 error. If you fail to reject the null hypothesis, you may have made a type 2 error. That's how it works, okay? So please note that if you failed to reject the null hypothesis, there is no way that you made a type 1 error, okay? So when you're done with a specific test, you either have the chance of creating 1 or 2 of the types of errors, not both of them, okay? So the homework in this section is basically going to say, I do a test, here's the result. What type of an error did I have a chance of making, okay? And your answer needs to be either type 1 or type 2, never both, okay?
So that's why they use the wider, like 85 to 90% of companies in the world, because it's a better chance of not hitting you.
Well, again, what it does is that it makes the chance of either of these happening, regardless of whether you reject or fail to reject, essentially equal, more or less. I mean, it varies based on the value of n and some other things, and we could get into math behind it, but it's really deep and it's a nasty rabbit hole. I mean, it would be really fun for me, but you would kill me if we went through it. And so I won't, because math is really scary. So just take my word on it that that's the way it works, and I won't throw the really nasty formulas at you that govern how this works, okay? And because it's integrals, it's over the continuous space that, never mind, I'm not even gonna go down the road. Okay, so just realize that these are the types of errors that you can create, and note when they happen, okay? And the homework for this section will basically just ask you that. So let's take a look at one of them and see what it asks, okay? All right, so
8 through 12 is what we decided.
8 through 12. Okay, so let's do number 7. So, a new whitening toothpaste advertises that it whitens teeth up to 3 shades whiter, whatever the hell that means. The product has been so successful that the company wants to change their slogan to more than 3 shades whiter. All right, so before they do so, they want to test the new claim with a hypothesis test, etc. According to the sample obtained, the decision is to fail to reject the null hypothesis if the toothpaste in reality whitens teeth an average 3 shades whiter was an error made with the hypothesis test.
Type 1. It says that they failed to, oh,
If they
Yeah.
fail to reject,
It's
and
a
it is 3 shades whiter, then there's nothing wrong.
Then there's nothing wrong. Exactly. So that question is basically saying that you validated what you claimed, therefore it's true. Okay? So there was no error in that particular value. So part of what you're also trying to do here, folks, is to realize when you don't make a mistake, and then when you do make a mistake, which one did you make, type 1 or type 2? All right? Does that make sense? It's a little bit weird that you're trying to sort of read into the problem that it's telling you that there wasn't a problem with the claim, and because there wasn't a problem with the claim is valid, and therefore it's a correct assumption that what they said was true.
So, okay, so when it says fail to reject, that's saying that they technically are going with it?
When they failed to reject, that means they failed to reject that it's not more than 3 shades whiter,
Right.
and therefore it is 3 shades whiter, and that's what they claimed. So therefore it's a correct statement. They didn't make an error at all, and therefore when you don't make an error, you won't have a type 1 or a type 2. Okay?
You said we had to have either or.
Well, in this case, when they're testing the claim and asking you, did we make a mistake, because they're saying the reality behind the situation, then you can be right or wrong. Normally in the real world, we don't know whether what we're testing is really valid. That's sort of the difference here. Here you're trying to say, yes, I know that something is true or false. So let's try another one. Let's try number 5 as well, because you guys have got the answer to that one in there as well. So what does number 5 say? Percent of children that leave foster care due to adoption is generally accepted to be 32%. A social worker claims that this percentage is incorrect. After performing a hypothesis test in the claim, he fails to reject the null hypothesis. In reality, the percentage of children leaving foster care due to adoption is 33%.
Type 2.
Why is it, first off, why is it in error?
Because it's not 32.
Because it's not 32%, and that's what we were claiming. Okay?
He failed to reject the null hypothesis.
He failed to reject the null hypothesis, and when you fail to fail to reject the null hypothesis and you made an error, what type of error do you make? Type 2. So that's the way you're playing this game, folks, right? When they do the test, it's either going to test that it isn't or is true. And if it is true, then it's correct and you can move forward. If it's not true, then you're saying, oh, I made a false claim, I made an error, and then you have to tell me which one of them it is, type 1 or type 2. All right?
I don't like this at all. I keep getting tripped up because it says what, he failed to reject it, so I'm thinking that it's a type 2 where he failed to reject it.
Because it is. That's what it is. On number
But
5.
then you said if it's one, then it has to be the other. I'm not getting this. Because like if you have one, it's the other one that you widen the percentage of, right?
Right.
Okay, so he rejected it, so it should be a 1 then, right? Because that's the one that's widening open.
Well, when you're trying to adjust these is when you're changing the alpha. And in none of these problems are we changing the alpha. So the chance of type 1 and type 2 are equally valid for all of the problems in this section right here. Okay? So we're not trying to increase or decrease either one of them. We're just trying to determine, based on the facts, what happened. Did we either come to a correct conclusion based on our test? And if we didn't come to a correct conclusion, did we make an error of type 1 or type 2?
So we're showing which one we did the error in.
Yes. So
Not
when
the opposite of which that we're trying to find.
Nope.
Or like,
Yeah.
okay.
When you see that there is an error, then based on whichever one of these two things you did, you made either a type 1 or a type 2 error.
Okay.
And since this problem said we failed to reject, and it was an error, therefore it's a type 2 error. If it said it was an error and we rejected the null hypothesis, then okay, it would have been a type 1. So this is purely a sort of flow diagram type of problem. There's no calculation anywhere. It's just valid assumption, valid test. If it's a valid test, yes, then the decision was correct and we're good. If the test is not valid, no, then we have to make a decision which error. It's either type 1 or type 2. And it's purely on whether or not we fail to reject or reject the null hypothesis, right? So in this one, we would reject the null. In this one, we would fail to reject the null. And those are the only 3 cases you can have, okay? So in these 8.5 homework or 10.5 homework questions, there's one of 3 answers. Either it was a correct test and it did what it was supposed to. It was an incorrect test, and then you have to base on your result whether it was type 1 or type 2. And that's all there is to it, right? You don't need to do anything else more than that. You don't read anything else more into it. Don't try and guess anything more into it. Just stop with one of those 3 and then done. Right, so we're just setting the table. That's all we're doing here. We're not trying to slam anything home.
What
Is
does,
that supposed to be 8.5?
10.5, sorry.
What does null hypothesis mean?
It's your assumed value. So the null hypothesis is always the assumed value. The alternative hypothesis is always what you are trying to test or trying to get a test of. Okay?
So, I mean, it's sort of not my best diamond drawing of Venn diagrams, trying to draw it in a scribble really fast. True. All right. Not bad? Okay. So that was just sort of a little break inside of the flow of doing testing to point out what can happen while you're doing testing, right? The two types of errors that you can make, type 1 or type 2. Testing variance or standard deviation. So if you think back to chapters 8 and 9, that's what we did after we tested proportions, is we would test variance. What?
So you're gonna reteach how to do that section?
It's gonna look very similar to what we did back in chapters 8 and 9 for dealing with confidence intervals when it came to variance. It's the same sort of concept. Please remember that when you're testing variance, you're testing a squared value. So we are going to start using chi-squared statistics again. So turning to table G or whatever it is. I think it's G, I can't remember right off the top of my head. It's in your little foldouts, right? It's G, right? Yeah,
Hold on, or is it in the back?
either one. It's also in that. Table G is in there somewhere. So table G is your critical values for chi-squared. Hey, Mike, what's up?
Where are you also?
We're in Monroe.
Awesome. Have fun.
Yeah.
Enjoy. I don't want to interrupt. I just heard your voice, so.
Okay.
We'll see you.
Yep, see ya. Mike's mostly in Milton, so I hardly ever get a chance to see him. All right, so remember, folks. This is how the chi-squared statistics looks like, right? It's the square of the normal distribution, so that there isn't going to be a plus and a minus like we had in our Z and our T scores, right? Z and T scores are really nice because we've got all that symmetry, whereas in chi-squareds we don't, which is annoying, but it's life in the city, all right? Note that you can have one or two tail tests based on whatever type of test you're doing. So this is also going to be very similar to the T statistic. Remember when we used two tail versus one tail testing? Same sort of a concept. If you are working on a greater than hypothesis test or a less than hypothesis test, it's one tail. If you're working with a equal to, not equal to, then it's two tails, right? Sigma squared greater than n, sigma squared less than or equal to n, or sigma squared less than n. Note I'm doing variance and not standard deviation here. These are one-tail tests. This one should be squared, yes. And so then if you're doing equal to, not equal to, I should have used a letter other than n that implies I'm talking about the sample size, but I'm not. It's just any number. And note the key to this When you're working on a one-tail test, we're going to use the alphas directly. When you're using a two-tail test, we're going to use alpha over 2. So we're going to have to split the alpha in half. And we'll talk more about that when we actually start diving into some real examples. All right? So this is just more of a reminder that the same sort of thing applies here. And again, just remember that these are not symmetric. So you're not just going to have pluses and minus values. You're going to be dealing with alpha and 1 minus alpha, okay? All right, so yeah. The chi-squared statistic that we calculate, folks, the formula is going to look very similar. Note that S squared is going to be your sample variance. Sigma squared is going to be what you get from your ho or your ha, right? And n, just like it always is the sample size of whatever it is that you're looking at. And everything else, folks, stays pretty much the same, okay? Note that there are no p-scores in any of this chi-squared stuff. You just basically have to do greater than tests or less than tests, okay? Please note that when you're checking the right-hand sides, this is always 1 minus alpha over here. The less than sides are always just regular alpha, okay? So if you're doing a greater than, you're going to look up chi-squared 1 minus alpha. If you're doing less than, you're going to look up chi-squared of just alpha. And again, if it's two-tailed, then of course both of those numbers are alpha over 2. All right? So when you look up your chi-squared critical, okay? Look up chi-squared critical. For greater than, use 1 minus alpha. For less than, use straight alpha. Unless it's a two-tailed test, and then you use 1 minus alpha over 2 and alpha over 2. Okay? So this is the one-tail version, and the two-tail version is just 1 minus alpha over 2 and alpha over 2. So if you're doing it a one-tailed test, you want to leave all of your alpha on one side, so you don't necessarily have to divide anything in half, right? But I want to make sure that you keep track of which one's giving you a value for the right-hand side of the chi-squared graph, and which one's giving you a number on the left-hand side of the chi-squared graph. All right? All right, so let's do one. All right. So, test that variance of new golf ball design is less than 2.2. Alright, so for whatever reason we're trying to claim that our golf balls that we're manufacturing have less variance in the distance that they go, so that you can be more accurate when it comes to deciding how far you're going to hit the ball, right? So if all of the golf balls always go exactly 205 or 204 or 206 yards, but never any more or never any less than that, that would be really nice. Again, assuming that you're actually a very good golfer and can sort of swing the club the correct way every time. Having played golf, I can attest that that is very hard. Golf sucks. It's a great sport if you just need to go out and drink with people in a little cart, but it would be a lot cheaper if you just, yeah, and ordered a cart in the bar to drive you around. All right, so let's suppose that I sample 30 golf balls and get a variance of 1.95. And I want you to test at the 0.05 significance. Okay, so what do we always do first? There you go.
If all I ever had to do was hoe and ha, I'd be great.
The cool part about it is that the ho and the ha is always 50% of every question. So like on the final exam, if you do the ho and ha first and do it correctly, you've already got 5 out of 10.
Great.
Because that's half your battle, is knowing what the hell you're supposed to do. Then doing it is the other half. Alright, so what's the ho in this one? Or the ha, whichever way you want to start.
The 2.2.
What about
Less than. So if the hoe is saying,
sigma
not
squared?
P.
Sigma squared.
There you go. Sigma squared is less than 2.2 for hoe.
This is what's assumed is true?
That's what I'm saying, that a new golf ball design is less than 2.2.
Is that what I want to show or what we assume is true?
That's what they assume.
So they assume that it's less than 2.2. So what am I trying to show?
That's greater than. Right?
Is that what I want to show?
No, we want to show that it's less than 2.2.
That's what we want to show. So where do we put the less than if that's what we want to show?
So that's the ha.
That's the ha. And that's where you have to be careful, right? If it's something that I want to show or I want to be true, that's the ha, okay? If I'm trying to disprove something that's assumed, then the assumption is your null hypothesis. So if sigma squared is less than down in the ha, the ho, and the other way that you can test this one, or the other way that you can kind of look to see which way I want to test, is look at my sample variance. My sample variance is less than. I am trying to get a value that's less than. That's sort of a director a little bit as to which direction should be going, if it's going to be one-tailed as opposed to two. All right, so find your chi-squared critical value. What do you need when you're looking up chi-squareds? It's at the 0.05. What else do you need when you're dealing with chi-squareds? Well, what's the value on the left-hand side of the table?
The 1 minus, or 1 minus the half. Double half.
What do I need in order to know where to look in the tables? Degrees of freedom. What are my degrees of freedom, folks? Technically, it's 29. No, 30 is close enough. No. P-values are for Z statistics, so it can't be a squared value, which is mildly unfortunate. So in table G, oh, we do have 29, sweet. So now which one of these am I looking up? Which column am I going to look up in? So we're on it. Our degrees of freedom is 29, but what are we using? 0.05. Why are we using 0.05? Why didn't you use 0.95 or 0.025? It's less than and it's one tail, right? So if it's less than and one tail, you're just going to look up the alpha value, and you want to be less than that value in for your critical value, okay? So at 0.05, 29 degrees of freedom, what's my chi-squared value? 0.05? No, yeah, that looks right.
So because the one side is a one tail and the other side's two, they split that in half and that equals the one side, right? Okay.
That's why in the two-tailed test you have the alpha over 2's and then do 1 minus it and whatnot. So now, what is my chi-squared calculated value? 30 minus 1 times s squared, right? Over sigma squared. What was 1.95, right? Yeah. Sorry, what did you say that number was?
25.7.
Are we less than? We are less than? Less than 42.557, yeah. So if our chi-squared is less than chi-squared crit, we reject. And since it is, we can reject the null hypothesis.
So would this go into what we did in the first section, we had to tell which one,
What do you mean?
from the one we just did in 5.
Oh,
We had to tell which type or not.
I could ask you what type of error did you potentially create by making this assumption, right? And
That would
since,
be the type 2.
because we
You
rejected,
failed.
since we rejected, we may have made a type 1 error.
Okay.
When you reject, it may be type 1. When you fail to reject, it may be type 2. So,
That was the opposite. I'm getting stuck in the fact that if you make one, I thought we had to make, that would make it open for the other.
that's just the adjusting of the value to try and limit one versus the other. Once you're in the statistic itself and calculating the data, it's either one or the other. And you know, no ifs, ands, or buts about it. Alright? So, what did I assign from that section?
It's 10, 6, 4, 8, 12, 16.
10.6, not 10.5. 4, 8, 12, 16. All right, so let's do number 11 then, the potato chip one. I got potato chips on the brain. So, potato chip manufacturer produces bags of potato chips that have a net weight of 326 grams. Because the chips vary in size, blah, 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 blah. Bags pass inspection so long as the standard deviation of their weights is no more than 3 grams. A quality control inspector wished to test the claim that one batch of bags has a standard deviation of more than 3 grams and thus does not pass inspection. All right, so
So we're testing that it's more than 3 grams, right?
mm-hmm.
So that's our hot rate.
Uh-huh.
So it'd be the standard deviation greater than 3.
There you go. And note, standard deviation as opposed to variance, folks. So note that that's sigma, not sigma squared. When you work in the statistic, you're going to have to square that number. So what's my ho?
It's less than or equal to.
All right. They sample 25 bags of chips. The standard deviation is found to be 3.4, not sigma, but S. And again, remember, use English lettering for samples, Greek lettering for population. What? And the level of significance is 0.05.
So to find our X, right?
Yes, chi. Chi-square right. So, what are my degrees of freedom first off? 24. What am I going to look up?
24 on the one tail.
One tail greater than 0.5. So what are we going to look up?
24 on the one tail side.
Note that there is no one or two tail side or anything like that, right? You're just looking up a number.
13.84.
I should really bookmark this spot, right?
In your folder.
Oh, that's long gone.
Painted on the walls.
Would be nice, wouldn't it? I absolutely agree.
They can put posters up all over. Got nothing.
That's because no glasses.
True. Sad but true.
Seriously?
Yeah.
Oh, crap. Did I give it to you the wrong way? Strike that, reverse it. I did them on the wrong way. These should be reversed. God damn it.
Thanks, friend.
You might be doing that now.
I have to fix the other one.
Damn it. I wondered why the numbers looked a bit wrong. I had them backwards. I'm sorry, folks. This should be 1 minus alpha. This should be alpha. I was wondering why I was doing everything backwards. Now I see why.
Trust me, I finally thought I was getting somewhere.
My bad. This is alpha. This is 1 minus alpha. And strike those and reverse it. Alpha over
over 2 is 1 minus alpha over 2. Numbers were in the wrong order, and I knew it was making a mistake. I couldn't stop myself.
So we use one,
So when you're doing greater than, you use the alpha level statistic. When you're using less than, you use 1 minus the alpha level statistic, whichever one it is, alpha or alpha over 2. Darn it. That was all me. You guys will all get a free pass on this one to some degree.
because you have another section above that that's all right there. Does that change all that crap going on there? The 1 and 2 tail test stuff?
This stuff is all the same. When it's 1 tail when you're doing less than, you're still going to use alpha. When you're 2 tailed, you use alpha over 2. That stays the same. It's just how you use them, which is this stuff right here. When you're doing greater than, you should use alpha. When you're using less than, you should use 1 minus whatever the alpha score is. And that's what I was doing backwards. That's why this number was so far away when it shouldn't have been that far away in my problem I worked on. So theoretically, folks, what should have been the real correct value that we looked up here?
17.708.
That really shouldn't have been 42 point, should have been 17.708. And theoretically, what did it do? We actually should have failed to reject. No, we made a type 1 error.
Look at that.
He's totally on me.
So then the chi-squared will be greater than chi.
Yep, chi-squared is greater than the crit, therefore we don't get to reject, and we have to say, hey, failed to reject the null hypothesis. I apologize. Completely backwards, strike that, reverse it, except there's a whole load of striking and reversing.
So we did the 1 minus the alpha over 2 for that one, or was it just
We just did 1
minus?
minus alpha because it's still 1-tailed.
Okay.
Here we should have looked up the 0.95, 1 minus alpha, instead of the alpha statistic. All right, did everybody fix? Sorry again. So now, since we're using a greater than symbol in this question 11, we are looking alpha equals 0.05. We actually look up the real 0.05 level value.
Or 0.415, right?
415. And again, my bad on that one. And what is our chi-squared actual statistic? Don't forget to square the numbers. Remember that our test was testing standard deviation, but our chi-squared is always based off of a square value, a variance value, if you will. So make sure you square the numbers. And note, now we're looking for greater than because we're testing at the greater than level. Is our chi-squared greater than our chi-squared critical? We are not greater than. So we fail to reject the null hypothesis again. All right, now, since I screwed that one up, I will do one of the homework problems. How does that sound? So what did I assign again?
4, 8, 12, 16.
4, 8, 12, 16.
4, 8, 12, 16.
All right. So how about I do number 16 for you guys then? All right. So number 16. The variance of temperatures in chicken incubators on a chicken farm is generally believed to be 0.5 degree. Manager of the chicken farm claims that the variance has changed. He randomly tests 25 of incubators, blah, 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 blah. All right. What's the assumption, folks?
So once generally, but that's our assumption.
Mm-hmm.
So that's going to be equal to 0.5.
Uh-huh. And so what's our ha?
Not equal to.
So this is a two-tailed test. Here we're going to have to deal with the alpha over 2's, if you will. N is 25. Standard deviation, be careful with that. They're trying to trick you. S is equal to 0.55, so make sure that you calculate S squared appropriately. So that's a very tricky question where they start with variance at the top and then give you standard deviation in the bottom. That's not very common. And do this at the 0.05 level of significance. So, note, two-tailed test. So we're going to use alpha over 2, okay? And we want to be greater than the critical value of alpha over 2 or less than the critical value of 1 minus alpha over 2.
Do we have this?
Uh-huh. Uh-huh, 0.025. And then the other chi-squared we're going to look up is 0.975, 1 minus that. So what's the 0.025 value? Yep. What's the 0.975?
I don't know if I'm on the right side. Go by me.
Making me nervous there.
Never mind, I don't know.
I should really bookmark that page.
.025, 24. 39.364.
That's what, like, minus equal from whatever.
And 1 minus .025 is .925. That's the 12.401. So it needs to be greater than the .025 critical value or less than the 12.4101 value. Okay, because that's the two tails, the two sides. It can either be more than the top one or less than the bottom one. So all we have to do is calculate our chi-squared crit. 25 minus 1. Yeah, chi-squared statistic. Remember to square that 0.55. And remember that the 0.5 is not squared because it's already been squared, right? So 24 times 0.55 squared divided by 0.5. $14.52, that's what I was getting.
So it's between, so then it's not,
So it needs to either be greater than the top one or less than the bottom one. Unfortunately, it is not outside of either of one of those, so what do we do? Reject if or less. Right, so it has to be outside of those regions. Alright, so I apologize for that hiccup. Totally had my brain backwards. So that was 10.6. I'm going to stop there before I screw up another section. Oh, we're out of time anyways, good. And I will hope to get some homeworks graded for the next class so I can give them back to you. Since you can't do anything outside other than mope.
I said that was, that's what you.